Hello everyone, my name is Wang Wenhao. Cooperated with Yu Xihang and Jiang Yilei, we finished a group work project in the summer research. In this research, Xihang and I focused on simulation, and Yilei were working on mathematical improvement. But in the presentation, Xihang and I will together introduce the whole project. I will mainly focus on the introduction and problem statement to help you to know what we did and the principle of the system. Our project's name is Finite-Time Distributed Coordination Control for Multi-Agent System. It's an academic word, so sounds so complex. In an easy way of understanding, this is to drive many drones to fly to our desired position. Many drones have different destinations and should communicate with each other, forming a system, so-called multi-agent system. This presentation roughly have 4 parts. Let's begin with the first, introduction. Multi-agent cooperation is important in autonomous driving, exploring dangerous environment, and so on. Till recently, various control problems has been introduced, namely concentric blocking, formulation, and disturbed coordination. In all these research directions, the goal of our project is to achieve finite-time distributed coordination control for multi-agent system. It means 3 parts of goals. The first, converge to the goal position. The second, collision avoidance. And the third, finite-time stable. By these 3 goals, we introduce 3 definitions. First, controller. Controller of, or we call it controller, is an equation about velocity. We use the controller to tell the agent you should move at this velocity. And the second, finite-time stable, is a mathematical proof that the time from the start to the goal position is limited. And after reaching the goal position, if it is slightly disturbed, the goal position, it can automatically return to the goal position. And the third definition, barrier function. How agents know they should move at what velocity? They need barrier function. Imagine there are rolling mountains like this. We desire a 2D function. The value of the function in the height of mountains. In XY plane, different position will have different height. And then we tell the agents, keep going low. What will happen? The agent will never go to the top of the mountain and will eventually stay in the foot of the mountains. In that way, we control the agents. We design the barrier function, we control the agents. For example, we set the v equals to negative gradient of barrier function as controller. If we don't want an agent to go to somewhere, we design the barrier function value trained to be infinity. So the agent won't get there, right? At goal position, we just need to set the barrier function value is 0. Generally speaking, in most cases, it is very likely that there is a term of negative gradient of barrier function in controller. Hence, they control the agent's speed will point to the decreasing direction of barrier function. Let's move to part 2. Problem statement. Now, n mobile agents in a circular with radius r0. Each agent is modeled as a circular disk with radius r. We assume that the network is always connected. That's to say, they can communicate with each other and they can get the velocity and the position information of each other. So we can use this information and the velocity and the position information. We can use it in controller. Besides, we construct a boundary by another m static agents as obstacles because they can't get out of the boundary. Now, the goal is to find the controller based on the barrier function, and that every agent can reach their own goal position without collision with each other. That's to say, minimum distance larger than 2r. Moreover, the disturbed coordination should be achieved in finite time. That's all for problem statement.
Next, we will introduce the research procedure of our project. The allocation of tasks is that Zhang Yilei designed the controller and barrier function, while Yuxian and Wang Wenhao finished the simulation part. Yilei designed the barrier function inspired by an essay we read. As we see, if the distance between agent I and agent J is close to 2 times of the radius, the barrier function will be too large. So we can ensure collision avoidance. And we also prove that the agents can converge to their goal positions since the goal positions tau I is an equilibrium point of the agents. What is an equilibrium point? An equilibrium point for an agent is a point such that the velocity of the agent is 0. Hence, convergence to the goal positions is ensured. Besides, Yilei also proved the finite stability of the setup by choosing the Lyapunov function, the same as barrier function Bi. If you want to see the detailed proof process, you can reach us after presentation. Now, let's focus on the simulation part. Simulation mainly tested one simple case and one complex one via MATLAB. In the simple case, 4 agents are randomly deployed in the workspace, and the original positions and goal positions are chosen at random. And in the complex case, the number of agents increased to 20, and the original positions and goal positions are set randomly as well. So the videos are as follows. Other than the aforementioned 2 cases, we artificially select goal positions and arrange them in the shape of CUHK. They can reach the goal position successfully as well. So this video is demonstration. Till now, we should make a summary of what coefficients are keys to success. Through hundreds of trials, we found that the radius of the boundary circle R0 and the coefficient Ki are very important. If R0 is too small, there is higher possibility for an agent to get stuck in the area near the boundary. If R0 is too large, the restriction may not be enough for the agents to stay in the circle and they may converge to infinity as a result. When it comes to the coefficient Ki, we notice that it is multiplied by the gradient of barrier function. So we could say that if it is too small, the tendency for agents to converge to the goal positions is too small. On the contrary, if it is too large, an agent is too stubborn to go straight away to the destinations rather than make a detour. Hence, it is easy for them to get stuck before converging to the goal position. All in all, in the summer research internship, we have investigated the distributed coordination problem with collision avoidance in finite time. To achieve this goal, we developed a controller for multiple agents. However, the drawback of designed controller is that there are some trivial equilibrium points. Considering the drawback, our future work direction will be focused on 3 parts. Firstly, developing a second-order controller for the multi-agent system. Secondly, discussing the situation where the destinations of the agents are dynamic. Thirdly, trying different and maybe more strict setup. For example, agents are not connected throughout time. Thank you for watching and hope you a good day.